Okay, so we calculate this summary of the age and everything is looking fine. And as I mentioned in the previous video, we are all set for k-mean clustering. Okay, so let's go back to our script. I also mentioned us another approach of doing the same thing that we did in the previous step, and that is using a function called AVE. So the way this function AVE works is very similar to the aggregate function right over here, but it does something else. You know, in aggregate, we got 4 rows. We got 4 rows for each year, and thereafter we had to do merge with teens. In this approach, we do not have to do any kind of merge. The way it works is it does the same thing as aggregate. It takes teenagers graduation year as a way to aggregate the data. It will aggregate age based on the graduation year. So there are 4 graduation years. So it'll bucket the all the ages across 30,000 data points. It'll put into 4 buckets, and then it will apply this function. And this function is nothing but calculating the mean after removing all the NAs. So that's what it's doing. Function fun is a function. It takes parameter x and then it applies mean on x after removing all the NAs. So na.rm is equal to true. That's what it's doing. And it will apply this function on all the 4 buckets created for each graduation year. And once it does that, it will generate the output, which will be 30,000 fields, elements long vector. It will put that into this variable called AVE underscore age. So um, the only difference between this and the aggregate function that we talked about over here is that here we get a data frame which has 4 rows. Here we get a number of rows equivalent to the number of rows which are there in teens data frame. So with that, once we run this particular function, and we put all the data in AVE underscore age, now we can directly go to the last step that we did where we use if else function, and we say, okay, if teenage is null, in that case take AVE underscore age, otherwise take the age that came with teens data frame and put that into teen age. That's all we're doing in this. So very similar to the previous approach. The only difference is you do not have to do any merge, and all the things are done in just 2 steps. One is AVE step where you create buckets just like with aggregate step, and you apply mean function, and the output of that is a vector with 30,000 rows in there, and thereafter you use if else function to use that average to fill in wherever age is missing, wherever age is NA. So very similar to the previous approach, but this is another approach that you can use. But since I've already used the approach 1, I do not have to do this again. And you have an option. Either you can go with approach 1 or approach 2. Okay, so now we are done with removal of all the NAs which were there in the data. We are done with the removals of the outlier. So let's run the k-mean clustering. Now, before we run the k-mean clustering, one thing that we have um, is that we have to standardize the data. We have to normalize the data, something that I talked about in the class. If you have some high values, k-mean clustering is not going to work well. So if you have an outlier or large value, it will pull the centroid towards that large value. So how to get around that issue? So one thing that we talked about in the class was z-score. The way to implement z-score in R is by using a function called scale. And before that, what we have to do is we have to select some variables which we believe are relevant for clustering. So for that, let's run this function. All I'm doing in this is I'm looking at teens data frame, which I've cleaned. All the NAs are removed, all the outliers are removed, all the dummy variables have been created. And I'm only interested in 2 columns going from 5 to 40. So 36 columns out of 40 columns. And I hit enter. And all those 36 columns and all the 30,000 rows are stored in a data frame called features. So features created. Let's look at the structure of features. Okay, so features has 30,000 rows in there and 36 variables in there. So that is the structure of features, and all the things that we think are relevant for clustering are in features data frame. Now, what we have to do is we have to standardize all these variables which are out here. So how to do that? Using z-score. So that's our next step. So for that, we will use a function called lapply and a function called scale. And let's see how that works. So the way it works is lapply applies a function on the list in a given data frame. So I mentioned multiple times in the class, data frame is nothing but a collection of lists. So if you look at this data frame called features, it has one list over here called basketball, another list over here called football, another list over here called soccer, another list called softball over here. Softball is the name of the list, and this vector is the value for softball. Similarly, volleyball is the name of the list, and then you have vector which correspond to volleyball. So this is how feature is a data frame which is comprises of list, and lapply will apply a particular function, in this case scales, on each of these lists. So scale is nothing but a way to calculate z-score. So this lapply feature scale, this thing will apply a z-score on this list, say tennis. So it will calculate the mean of all these vectors, and then it will calculate how far away 0 is from the mean, and then divide by the standard deviation for tennis. And it'll do it for each data point, this data point, this data point, this data point, this data point. So the output gonna be of the length that is of the entire data set. So the output gonna be 30,000 observation long. And the output of lapply is a list. So what I have to do is I have to convert that into a data frame. So that is where as.data.frame comes into the use. So as.data.frame converts a list into a data frame, and then I store that into feature underscore norm variable. So let's run this. Okay, and let's do the structure of features underscore norm. And here, if you look at the previous structure, it was 0, 1, 1, 1, 0, 0, 0, 2, and all these. It has been replaced by something else. It's negative 0.3832. So all these numbers are very close to each other. Instead of just 0, it is like 0.332. Now you see negative over here. Negative implies that's below the average. If it's exactly the average or the mean, it would be 0, because that's what the z-score means. If it's a positive number, that implies above the average. So that's the way to comprehend z-score. So now my data is clean. My data is normalized. Now I can apply k-mean clustering. How to run that? So the way to run that is through using a function called k-means. However, before I do that, let me do one small step, which is set the seed. Why I have to set the seed? If you remember the conversation that we had in the class, the way k-mean clustering works is that you have to pick up three. In our case, in our slides, we picked up k is equal to 3, so 3 random points. If you want to create 5 clusters, you have to pick 5 random points, and thereafter the k-mean clustering will work around those 5 or 3 or 4 random points and will create clusters. So that implies that every time we run the clustering algorithm, like k-mean clustering, we'll have different clusters, slightly different clusters. And in case we have to reproduce the results, we won't be able to do that, because every time we run the algorithm, it's going to be different result. So in order to get around that, we do something called set seed. So with set seeds to be 3, 4, 4, 5, every time we run, we'll get the same set of 5 random numbers, same set of 3 random numbers, depending on what our k is. So if our k is 10, we'll get the same set of 10 random numbers. So that's the whole point of setting the seed. Even if you do not set the seed, still the k-mean clustering will work. However, if you try to reproduce the results, it's going to be a problem. So we are done with setting the seed. Now let's run the k-mean clustering on the data frame where we normalize the data, which is feature underscore norm, and we are choosing k to be 5. So that's what k means the function, it will run on this particular data frame called features underscore norm. The k is 5. Hit enter, and the output will be stored in a variable called teen underscore clusters. So while it's running, why we chose 5, not 4 or 3? Here I chose it randomly, but in the class I told you, the way to choose k to be 5, 3, 4, or 10 is by doing the analysis of first running k-mean for 2, 3, 4, 5, 6, 7, and then look at how the sum of square decay. So where the sum of square stops reducing, uh, the optimal number of k resides somewhere in there, and that's called elbow rule. So the decrease in the sum of square will look like an elbow. Wherever the elbow bends, your optimal k is somewhere near that bent. Okay, so it's done, and we can also look at the class of teen clusters, what kind of output this produces, and it's a kind of its own. It's called k-means. Now, this teens cluster has a lot of information about the model. So let's look at one of the information, which is called centers. So, so this is the information about centers of 5 clusters that we have created. Each cluster is associated with 36 variables because it shows 36 variables, which is right over here. When we created features, we chose 36 variable from variable 5 to 40. So, so those are the centers or centroids of a cluster. We can also look at the size of the clusters that we have created. So teen underscore clusters dollar size. So if we look at the size, there's one cluster with 871, another cluster with 600, another cluster with 5981. There's a huge cluster which is 21,514. So that gives a estimate about how many data points are there in each cluster. Now, there is no cluster that has only like 10 or 15 or 20 data points. Of course, there's one cluster that has 600 data points, which is a sizable number. Had it been 10, 15, in that case, we should have decreased our number of clusters instead of 5 to 4, and that way those 15, 20 would merge into one of those 4 clusters. But that is not the case over here, so we should be fine. So this is a way by which you can find out the details about your k-mean clustering model. Now, one thing that I want to do is I want to write out the centers of this k-mean clustering model so that I could visualize it in Tableau. So how to do that? Now for that, there's a function called write.csv, just like read.csv, and I can write out things in CSV format. So this is the syntax for that, write.csv teen underscore cluster centers, and I'll write it into a file called center.txt. I can make it CSV if I want. And now this file has been written to my my working directory, which is on the desktop. So let me go to desktop, RLAB03, and I see center.csv right over here. So this file has been created. I can open it in Excel, and I can see, okay, this is all the information. These are the cluster names, 1, 2, 3, 4, 5. I can populate this to be a cluster because I know it's clusters. Okay, and I can save it and click yes. And so this is cluster 1, and this is you can say this is an address of cluster 1 centroid. And we'll save it. Okay, so everything is saved. So that is all done. Now, along with that, what we can do is we got all these clusters and their centers and everything. Now we can go back to our original data frame that we started with, which is teens, and we can populate the clusters in that data frame so that I could say, okay, this individual, his gender is female, and very interested in tennis or swimming or shopping, and he or she belongs to cluster 2 or cluster 1 or cluster 5. So in order to do that, all I have to do is to execute this statement where I create a new variable in teens data frame called cluster, and I will give it all the clusters which are there in teens clusters. So let me just do this. And now uh, teens data frame has one more variable called clusters, and it has all the clusters which were calculated by the k-mean clustering algorithm. So let's do structure on teens and let's see how it looks like. So it has, you know, one more variable in there called clusters, and it goes 5 3 5 4 4 4. So I can do actually something like table on dollar teens dollar cluster, see what it looks like. It should it should match with the size of the clusters. Okay, so it does match. So the first one has 871 seconds, 600, 5981, 103, 421, 514. Um, so that's what I've done. I took all the clusters which were there in my teen underscore cluster, which is nothing but the model that I created at a k-mean clustering algorithm, and I assigned the clusters to the original data frame teens, which has all the data in there. So now I can see, okay, this person one, all the attributes of person one, and that belongs to cluster two. Then second person belongs to cluster three. Fourth person belongs to cluster five. The reason I want to do it this way is because I want to understand the characteristics of the cluster. You know, what's the difference between cluster one, two, three, four, and five? So that's the reason I want to do that step. Also, if I want to look at the first five records of my teens data frame, which now has clusters in there, along with the information of cluster, I can do something like this. Here, what I'm doing is I'm saying give me 1 to 5 rows. And in terms of columns, I'm only interested in clusters, genders, age, and friends. So now I know, okay, the cluster is the one, its cluster is 5, and the gender is male, and the age is 18.982, and the friends are 7, and then cluster is 5 over here, and the age is 18.875, and that person is female, and there are no friends. And then cluster 4 has no gender, and the age is 18.995, and 10 friends. So now I can visualize the entire data. I can go through the entire data, and I can say, okay, what's the difference between cluster 1, 2, 3, and 4 and 5? Something that we did in the class with the marketing data, where I had 4 pictures and 4 clusters, and I can see, okay, how these clusters score across purchase frequency versus return rate versus lifetime value. So this is something that we can do. At the same time, I can also calculate some aggregates on the data based on the cluster. So what is the mean age of the cluster 1, 2, 3, 4, and 5? And that'll give me more insight into how cluster 1, 2, 3, 4, 5 are different from each other. So let's look at the mean age. And all we are doing over here is again calling functional call aggregate that we used in one of our steps. And I will aggregate data called teens. I will aggregate by cluster. So if there are 5 clusters in there, I'll create 5 buckets. And for each bucket, I will work on a variable called age, and I will calculate mean on age. So, and there's no na.rm because I know that at this point in time, everything is clean. So we don't have to do that. And once I run that, now I got 5 rows in there for each cluster, and then um, and then their respective average age. So one is all the young people. Okay, so one is all the young people, 16.86, and 2, 3, 4, 5 are older people. I think the oldest are in second cluster, and then the third one is 17.29. So second in terms of age is 17.29, and the youngest is of course the cluster one, 16.86. Those are young people. Others are much older than cluster one. Okay, so that is one way. Another thing I can do is I can do the same thing, but instead of clustering by age, I can cluster by gender. So let's see in terms of female. If you remember, female is a dummy variable, so it has um, values 0 or 1. So all I'm saying over here is aggregate the data called teen and divide the data into as many clusters are there. So there are 5 clusters, divide them into 5 bins, and on each bin for variable female, calculate the mean. So for the cluster 1, it's 83 percent people are female, 2 is 72%, 3 is 83%, 4 is 80%, 5 is 69%. So it seems like 5 is the least, is a cluster that has the least number of females, and um, and 1 is one which has the highest number of females in there. Okay, and third one is the same kind of thing, but in this case, I am doing the same logic, but on friends instead of age or female. And I get, okay, the first cluster, the average number of friends are 41, the second is 32, third is 37, fourth is 30, and the fifth one is the lowest one, 27. The same thing, like you can look at the clusters, aggregate them, see, all we are trying to do is to find out characteristics why cluster 1 is different from cluster 2. Okay, now so far so good, but there's one thing that I talked about in the class, and we briefly talked about here also, how to find out the optimal number of k. And for that, there are a number of ways of doing that, but I've written my own function that I use all the time. It's a very simple function, but you can also write it if you want, or you can just cut, copy, paste, and use the function that I've already written. No need to reinvent the wheel. So what I'm doing in this function is that I take two parameters. There's one data frame that I take on which I have to calculate the optimal number of k's, and then um, the k, which particular k that you want to run with. So the maximum k. So if um, if you're thinking of k to be 5, then take x to be like 15, and that will give you the sum of squares going from cluster 1 to cluster 15, and then you can plot 1 to 15 and see, okay, where that elbow bends. So that is what I'm doing over here. So I take two arguments. One is data frame, and x is the k, the maximum number of clusters that you want to examine. And thereafter I declare an empty vector. So y is an empty vector, and thereafter I create something called for loop. So for I in 1 to k, so if let's assume k is 15, or let's assume k is 20, so this loop, which starts from here and ends over here, will run 20 times because x is 20. So I will go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. It will do 20 iteration. Each time its value will get incremented by 1. So again, I will set the seed to be 42 because I want my clusters to be same again and again and again. And thereafter, I'll run the k-mean clustering algorithm, where I will call k-means function as we did in our exercise, the data frame on which I want to apply k-mean, and which particular k I want to apply k-mean on. So the first time this loop runs, it will be 1. The second time it will be 2. Third time it will be 4, 5, 6, and then will go to 20. So every time it runs, it will put the output into a variable called k clusters. And thereafter, I will sum the within some sum of squares of that k clusters, and I will put into a variable called sum WSS. So this sum WSS has the sum of squares of all the clusters. And thereafter, I will use rbind, which is a way to bind two rows. And this will have two values in there. One is the k that I used for this iteration. So if it will go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to 20, and then some WSS which I calculate for that particular k. So at the end of the day, if my k is 20, or this x is 20, I will have 20 rows in y, and this I will be from 1 to 20, and then for each cluster k, um, I will find out what is the sum of square. And then I create DFT to be a data frame, and then I use a function as.data.from data.frame that we have used multiple times in our class, and I will convert this y, which is going to be matrix, into a data frame. And then I change the column name of this particular data frame. The first column will be called cluster, so I will be the cluster, and then the second sum WSS will be called within SS. So the output gonna be, and then I do print of DFT, which is printing the data frame that I just created. So if I run it, if k is 20 or this x is 20, I will have 20 rows in this data frame going from 1 to 20. And for each row, I will have the within sum of square for that many cluster. And all I have to do is to plot the output against each other, and then I'll get that line that I showed in the class. And then we'll look for that proverbial elbow bend. So uh, I'll do all these things, which is written in this function, and I will call this function optimal k. So we have already declared this function. Let's plot, and let's run this function first. And I'll run it for, so here I say 15, but let's run for 20 because I've been talking about 20 for so long. And let's wait for a while because it will do 20 iterations. It will run k-mean clustering for one cluster, k is equal to 1, then we'll run for k is equal to 2, run for k is equal to 3, 4, 5, 6, and so on and so forth till it reaches 20. So that's the reason why it's taking some time. But once it finishes, X will have the data frame that we talked about. And it will also print the data frame right over here so we can see what exactly is there in the data frame. Still running. And meanwhile, while we're waiting for this to finish, what we can do is we can start Tableau because we want to examine those center.csv that we had created. So go to the start window and then type Tableau, and Tableau will come up. Okay, so we got a warning, but that is all fine. But here is the output that we got. So it ran with cluster 1, and this was a sum of square. And if you look at, say, cluster 5, the sum of square is way lower. It's almost like, from 107, it became 95. So there's a drop of almost like 13,000 right over there. And then it decreases hereafter, but not that much. So if you look at cluster 10, the drop is only of about 10, 11,000. So it's not that much. So thereafter, the drop decreases somewhat, and it takes 20 iterations to go from, say, so here we were 10, so 84. Even after next 10 iteration, it only drops by 10,000. So definitely it's slowing down. So now what we can do is we can look at this data frame and we can plot it so that we could visually see like how the data looks like. So for that, let's go to our lab and let's run this argument, which is plotting. X is the cluster, number of clusters, and Y is the within sum of square, and we'll use type is equal to B, which will have dot and a line going through it. So let's run this statement. And this is how it looks like. So if you want to zoom it, we can click over here and it zooms it. And if you look at 5, I mean, till 5, the decline was much faster than after 5. But once again, I mentioned in the class, the best clusters are those which have some business meanings. So uh, I picked 5, and because I felt that after 5, the decline is kind of not that dramatic as it was before 5, but you can play with these number of Ks and keep looking for the business meaning. So it may happen that right over here after you can take say 4, and or the 4 is right over here because there was a decline and thereafter it became not so fast a decline. So maybe you can run with 4 and uh, show it to your domain experts and look at the characteristics. If there's a better segregation of the data at fourth uh, cluster, then it makes sense to run with 4. However, if you see that there's a better insight with 5 cluster, then maybe run with 5. So elbow rules, as I mentioned in the class, may not be all the time as distinct as an example we had in the class. Many a times you have to you have to think about how fast the data is decreasing before that particular point versus after that point. So if after that point it decreases, that implies that that's the point where you should go for K. But this is a way by which you can find out the optimal number of K. Okay, so my Tableau is open, so I'll open a text file. I'll go to desktop and I'll go to RLAB03. I'll pick center.csv and and it's opening up. Okay, so now center.csv is open. It's loading the data. Okay, so data is all loaded. I'll go to sheet. Now, the first thing that I have to do is have to convert this cluster into discrete, or I can take the cluster, move it over here. It will become discrete by itself because cluster is discrete. It's 1, 2, 3, 4, 5. It's categorical. It's not continuous variable. Okay, and so I'll take cluster right over here. So I got 1, 2, 3, 4, 5 clusters in there. Okay, and then I will take all the features that I selected and I will push them right over here. Okay, so this is how it looks like, and and we have used bar graphs by default. So far so good. Now what we can do is we can look at each individual cluster and we can pick up some sense, how these clusters are different. So let's look at one of the cluster which is big on Abercrombie, and what kind of people are they? They are not interested in band, and this is cluster one. They're interested in Abercrombie. They're low on baseball. They're high on cheerleading. Okay, and they're okay on sizable, moderate on clothing. And what else they're big on? So another retail store, they're onto that. They're very much into this word or phrase called hot. And then mall, they're big on mall. So if I am, and then shopping, they're big on shopping. So that's another thing they're big on. And the tennis, swimming, volleyball, they're kind of in there. But one salient feature about cluster one is that they're big into shopping, mall, and things like Forever 21 or Abercrombie. So if you are Forever 21 or H&M, cluster one is the one that you should go after in terms of your marketing campaign. Now let's look at something else. Let's look at cluster three. So these guys are high on baseball, basketball, well, high on Bible as well. So high on cute as well. So dance is okay. God, football is high, and then mall is moderate. Music is moderate. But if you look at tennis, swimming, volleyball, they're high on that. So if you're thinking of going after, if you're a sports authority and you want to target those people who are interested into sports, this is the cluster you should go after. Okay, now let's look at fourth cluster and what they are good for. So baseball, they're interested into basketball, not so much. And then clothes, they're interested into dresses, drugs, drunk. So it looks like, um, and then kissed, they're high on, mall, they're high on, sexy, they're high on. So if you look at all these attributes, these are the people I would say, they need some counseling, some kind of guidance. They're not going the right way. But that's another category. It's very much visible through the data. And then we got a group that is not that attractive. Everything, they haven't formed their opinion yet, or they're kind of introvert. They're not that much onto Twitter or Facebook, and um, they're not high on any of the things like whether it's clothing or whether it's shopping or sports. So you shouldn't waste your dollar amount on targeting these guys. Now, the whole purpose of this exercise in visualization is to give you a technique through which you can visualize a cluster, because clustering is not that big a deal. We've already gone through the salient feature of how to do clustering. You take the data, you clean the data in terms of recoding, in terms of creating dummy variables, in terms of imputation, as you did with the age variable, and thereafter doing the normalization, for which we use z-score. You can create another normalization function, which is something like look at the range, like min or max. So you take a subtraction of min and max, that'll give you the range. So that'll be, instead of standard deviation, use that range, and then look at how far your point is from the minimum. So minimum minus or your data point minus minimum divided by the range. So that could be another normalization method instead of z-score. In case you find out your data is not normally distributed, you can go with that z-score definition. So you normalize the data, you run k-mean clustering, you look at the centers, and then you visualize the center to find out what's so special about these clusters. So it may happen like here, I already ran a bunch of times and I knew that five it will work great, and it produces much better visualization. It may happen that you will run with 6 or 7 or 8, and then you realize, there's not much difference between, say, cluster 7 and 3, and so maybe I have to reduce K. So you'll go through, bunch of iteration, but this is the strategy. This is the way by which you run k-mean clustering.